So thank you very much for the introduction and for the invitation to come and talk here in Dublin to give the annual Statutory Public Lecture. It's a real pleasure to be here. And as you heard, I'm going to talk about gravitational waves today. Gravitational waves, as it says in the title, a new astronomy, a really different way that we now have, after many decades of working towards it, to study our universe, to study our dark universe. So we're going to talk about gravitational waves you're familiar with on the whole from everyday life. The first one of those on the list is, of course, gravitation. And then, of the four, the other one that you're typically familiar with is the electromagnetic force. The other two, the weak and the strong force, typically we don't experience in everyday life, and that's because they act over pretty short distances on the whole inside atoms. But the other two, gravity and the electromagnetic force, we kind of have a feel for this strength because we can experience those forces. Now, gravity up there, you've got a pretty good feel for what gravity feels like, because you know what it feels like if you jump up and how you come back down, or if you pick up an object and let it go and it falls under gravity. So you kind of have a feel for what that's like. So let's call that in arbitrary units 1, a strength of 1. The electromagnetic force there then, which is the force that's relevant when you've got a magnet and you hold it up to the front of your fridge and it sucks onto the front of the fridge, is 10 to the power 37 times roughly stronger than the force of gravity. Now that's enormously stronger, so that's scientific units. If it was 10 times stronger, it would just say 10 there. If it was 100 times stronger, it would be 10 to the power 2, 1,000 10 to the 3, 10,000 10 to the 4, and so forth. So 10 to the 37 times stronger is almost unimaginably stronger than the force of gravity. But yet you know, if you take the magnet from your fridge and you just pull it a bit further away and let it go, it will fall to the floor under the influence of gravity. So despite the fact that gravity is so much weaker than the other forces, on large scales, gravity wins. Gravity is relentless. And the reason for that, in that case, is you know that in your magnet there's a plus and a minus. You can make magnets attract or repel, but gravity is always attractive. So the gravity from each piece of matter is attracted to one another. Gravity is always attractive. So the forces from individual particles all add up. So as you pull that magnet away, on the whole, at some distance from it, the fact it's got a plus and a minus means that it stops being relevant, and what takes over is gravity, despite the fact it's so weak. So on the scale of our universe, on the scale of the galaxy, gravity is exceedingly important. And we say that gravity is responsible both for the birth of stars and the death of stars. You could say for the fact that we exist. Again, out in the cosmos, there are clouds of dust and hydrogen, individual particles all clumping together to form larger clumps, eventually forming the stars, fusing in the middle, and the cosmos as we know it. And how things move under gravity is described by Newton's law of gravitation. And it's pretty simple, Newton's law of gravitation, and in fact, for many cases, for many things we want to do in terms of calculating how objects are going to move under gravity, Newton's law of gravitation does just fine. And it's quite simple. It says that if we have two objects, two masses, they will be attracted to one another with a force that depends on the mass 1 and mass 2, what their masses are, and how far apart they are. And that's what Newton's law says. But it has a rather unattractive feature, which I think even at the time Newton recognised, which is that when those two masses, again, feel an attractive force, gravitational attraction that depends on their mass and their separation, if their separation changes, in Newton's theory, the force between them changes, and it changes instantly. There's instantaneous action at a distance. And so practically, if one of those masses was the Earth, and the other mass was a star on the far side of the universe, there'd be a gravitational attraction in principle, and if that star changed its position with respect to us here on the Earth, we would say that no information can be carried faster than the speed of light. And that's no information, and that includes gravitational information. So actually, special relativity tells us that there must be travelling gravitational signals that are not travelling faster than the speed of light. So no matter your favourite theory of gravity, special relativity tells you there must be travelling gravitational signals in the universe. There must be gravitational radiation. And then in his theory of general relativity, Einstein wrote down mathematically a framework to describe gravity in the universe, and indeed predicted in more detail what these travelling gravitational signals look like. And you'll see the picture here, again, it's a one I particularly like to show because it's Einstein in Glasgow. It's Einstein in Glasgow in 1933, where he was collecting an honorary degree from the University of Glasgow, and he gave a lecture. He gave the first in the series of Gibson lectures. And you can see here, it was written up by the university press at the time, and he gave a talk on general relativity when he was there. And there's a couple of things. Again, one thing I also like about this photograph is that, again, when I put it up, you instantly recognised Einstein in the picture, because he's in full fuzzy-haired iconic mode at this point. Everyone else in that picture, again, was either the principal of the university or also getting an honorary degree at that time. And written underneath, you won't be able to read, but actually the person on the far right here was the Archbishop of Armagh in all Ireland. I think that perhaps was him, and I'm about to prove my own point. On the end, there was actually the former Prime Minister of France. So there's both, again in the picture there at that time, a very well-known politician and a very well-known man of the cloth. And yet today, if we went out into the street and we took this picture and we showed it to people outside, I'm pretty confident the only person that they would recognise in this picture is Einstein, and that they would be able to recognise him. Now, this always cheers me up when I think of this. As a scientist, that after all these years, the person who in this picture remains in the public mind for his achievements is Einstein. It's the scientist. Again, now that might just be, of course, the power of good hair rather than science, but I like to think it's the power of science. And it reminds us that as scientists, we can, again, even with what looks like and what is, again, a fairly complicated theoretical treatise, leave an impact that is long-term and long-term on the public. And I'm happy to expand on that in a bit. But for our purposes, again, Einstein gave a talk on the theory of general relativity. Now, that's now long enough ago in 1933 that there's pretty much no one left who was there and remembers Einstein's talk. But rumour has it, it was pretty incomprehensible and nobody really understood much of what he was talking about. And it is, of course, a complicated theory. Now, I'm confident that my colleagues in the Institute for Advanced Studies and the Theoretical Physics Department here could do a fine job of explaining the theory and the details behind that. I will own up to the fact that I'm an experimentalist, and so I don't find it terribly illuminating to look at the maths, but I am interested in the physics behind it and in what it tells us about what we can measure in the universe. And in fact, we are fortunate that general relativity is a geometrical theory, and we can describe what it tells us in geometrical concepts. So if you imagine this framework is measuring out points in space, measuring the distance between points, if we then add some mass to space, general relativity tells us that that mass curves space-time around it. And so it actually, in this picture, distorts the markers of space, the positions in space. We say that matter curves space-time. Then, if we came along and we added a second object to our universe here, that object would follow the curves of space. So in general relativity, we can picture gravity as the curvature of space caused by mass. So when we have two objects, again, that appear to be attracted to one another, they're actually rolling down the curve of space-time. So if we, instead of looking in 3D, we look in 2 dimensions, it would try and roll down the curve towards the first one. They'd actually roll together slightly. So the curvature of space we can picture in general relativity as gravity. Now, if we imagine that that mass actually moves, it wobbles, it does something catastrophic, it's a star and it explodes, it will change the curvature of the universe round about it. It will send out ripples across this rubber sheet. And those travelling ripples in the curvature of space-time are gravitational waves, carrying with them information about what produced them. We said gravity was responsible for the birth of stars. It's also responsible for the death of stars. So in a star, a bit like our sun, in the middle, the atoms, the hydrogen atoms, fusing together and giving out energy. That energy is actually balancing the force of gravity, which is trying to cause the star to collapse. And those things remain in balance until eventually, of course, the star will run out of hydrogen and then helium to fuse. Gravity wins, the core collapses into a region of space that's much smaller. Again, depending on the size of the star, the subatomic particles, the protons and electrons are forced together to form a neutron star. Again, a star made of material under such densities and pressures that we can't create that material here on Earth. We only can study it in space. Huge energy is given off in this as the outside's blown off and we see a bright flash, a supernova. If the star is large enough, the core may collapse down into a region of space where gravity is so strong that nothing can escape its pull, not even light. And that region of space we give the name a black hole. So you can imagine an event like this, again, should distort space around it, send out gravitational waves. And those we are interested in studying, since pretty much everything I described to you we get from trying to deduce what happened inside the core of the star when it collapses, from looking at the signals that are close to the outside. Gravitational waves are caused by the motion of matter itself. So if we can sense those, we can get information about the mechanism, about that stellar collapse, to sort of see into the heart of the collapse. We said one of the endpoints of a supernova is a neutron star. And inside this is the Crab Nebula, this lovely glowing a mass of dust and gas, which is the remnant, the leftover sort of a remnant of the explosion of an ancient supernova. And we believe in the centre of that, there is indeed a neutron star that's rotating. And that neutron star has, round about it, still some magnetic fields. So any charged particles that get caught in that get accelerated and they produce radio waves. So there's kind of a spinning beacon of radio waves sending out radio signals as that star spins in the middle. Every now and again, one of if we're lucky, that radio beam passes us on Earth like a lighthouse, and we can tell, again in this case, that that's what we believe, artist's impression, is in the centre there. If that's not perfectly spherical, if whatever makes up the neutron star core has different properties, again we have different theories for what's inside there, it can sustain different size lumps on the surface. You can imagine that spinning star in space with a lump sending out gravitational waves, dense in the curvature of space-time as it spins. Those, again, we would very much like to detect because we simply don't know what state the matter is inside these objects. Space is our laboratory. We can't simulate it here on Earth. There are densities and pressures that we can't replicate. And again, it's pushing the boundaries of what we understand. If we have two neutron stars, two compact stars, caught in one another's gravity, as they roll around in our universe and distort space-time around them, they will send out gravitational waves, losing energy through those gravitational waves as they propagate out, with the stars getting closer and closer together, spinning faster and faster, until eventually they reach a point, again, where they actually collide and give out a burst of gravitational radiation. Again, why are we interested in objects like that? Well, general relativity is a pretty comprehensive theory of gravity, but we know it's not the full story. We can't unify it with all those other forces. Systems like this, with neutron stars or pairs of black holes, are gravity in the strongest conditions that we can imagine. Again, they provide a laboratory to study what's happening in systems where gravity is exceedingly strong. And even before we made our detection, we were confident that such sources should produce gravitational waves. There's a very famous system called the binary pulsar, where again, through looking at the radio signals from a star in a binary system, using the radio telescope you see there, these two scientists, again Hulse and Taylor, made a set of observations measuring how the orbit of that pair of stars was changing over time. You can see here between 1975 and 2005, but the measurements actually continue. And the plot here shows both measured data points, which are the points here, and the plot, the prediction from general relativity about how the orbits of that pair of stars should be changing if they were giving out gravitational waves. And you can see it fits beautifully. And this observation got them the Nobel Prize, which is perhaps why they're looking so happy here, and they've got the glasses in their hands, because it was wonderful confirmation of the belief that these systems should produce gravitational waves. So up the left-hand axis here, it's actually showing the decrease in the time it took for these stars to reach closest approach. So we believed those star systems for many years should produce gravitational waves. But the sorts of sources that I've talked about here are just a set of the possible kinds of things that should produce gravitational waves. In the same way, when we study optical signals from stars, that's only one kind of signal that the stars are giving out to look at with telescopes. In electromagnetic astronomy, there's optical, X-ray, gamma ray, radio waves. Gravitational waves also come with a variety of signals from a variety of sources, and everything I talked about actually is just here. And I'll mostly talk about that in the talk today and the detectors that we use to make those observations. But there are other exciting sources I'll talk a little bit about, for which we need effectively different kinds of gravitational telescopes to study those. So, again, the source of particular interest for us at the moment is not two neutron stars colliding, but two black holes colliding. And this animation shows, again, two black holes curving the space around them, again, just in 2 dimensions, producing gravitational waves, getting closer and closer together until eventually what we call event horizons of the black holes merge and a new black hole is formed. Now I'll run that again because underneath there's a signal here, the signal that we expect from that sort of event. So as the black holes are orbiting some distance away, what you see underneath is a trace of how they're stretching and squashing space-time. What we would measure sitting a long distance away from this, measuring the distance of that grid in space between 2 points stretched and squashed together, faster and faster, with a larger and larger signal, till eventually the black holes collide and then wobble slightly. There's a little wobble of space, sending that signal out across the universe. And that signal, you can see, is very much what we saw and reported in February this year. So these plots are plots from the paper, from the published paper from February. Again, it's free to download, it's open access. And at the top, you can see traces from the 2 LIGO observatories that were operating at that time. On the left, you'll see there's one in Hanford in Washington State. On the right, again, overlaid the signal from the observatory in Livingston in Louisiana in the United States. And the top trace there is the signal from the instruments. That's the stretching and squashing of space due to 2 black holes. Underneath, you can see, and that's with only minimal filtering from the instruments. Underneath, you can see our best fit template to two black holes merging, spiraling in and colliding, again, fit to that data, and they fit beautifully. And what does that tell us? What was it that we actually detected? Well, you can see there, again, if we compare that to our black hole system and what we expect from colliding black holes and how they're stretching and squashing space, it's a beautiful fit. And this is the in-spiral phase where the two black holes are circling round one another. We see the last few cycles of that in-spiral as they merge and a new black hole is born. And the reason that observation, again, was so exciting is a number of reasons. It was, again, one of the last unshown predictions of general relativity, direct observation of these signals. It was the first observation of two black holes like this in a system spiraling in to collide. And again, quite remarkably, again, when we look at the numbers, detected in the 100th anniversary year of general relativity, which was last year. The signal arrived on 14th September in the morning last year, 100th anniversary of GR, and announced this year in February 2016, which is the 100th anniversary of Einstein's prediction of the existence of gravitational waves. So it arrived just in time, it turns out. And it was remarkable, again, and from that chirp, from that signal, encoded in that is the properties of the signal that produced it. We can tell the masses of the two black holes before they merged, one about 36 times the mass of our sun, the other 29. We can tell the distance to the black holes. Again, in astronomical language, about 410 megaparsecs, which, again, maybe a bit more intuitively, is about 1.3 billion light years away from us here on Earth. Again, where a light year is a distance, it's the distance that light travels in a year. So 1.3 billion light years away. All of that's encoded in the signal here. In addition, encoded is information about how the black holes were spinning. It's information about the final black hole that was born, 62 times the mass of our sun. Now, for those folks paying attention, that if you add up the individual masses of the black holes, it doesn't come to 62, it comes, I think, to 65. 3 times the mass of our sun was radiated away in energy. That's a huge energy produced actually in an event that was almost certainly completely dark, gave out no light whatsoever. We can tell the size of the black hole that was formed. It's about 366 kilometers, which turns out to be about the size of Iceland, spinning about 100 times a second, so that a point on its edge, on its event horizon, was traveling at nearly half the speed of light. We can also tell, not on the slide there, that it's not a perfect sphere. It's actually squashed slightly, again, due to the fact it's spinning, about 20% different in its different directions. And all of that is we can extract from the signal. And again, we said earlier gravity was very weak. We need objects like this with very strong gravity to produce measurable signals. But the fact it's weak, that gravity interacts weakly with matter, in the case of doing astronomy with gravitational waves, also has a benefit. It means that the signals, when they arrive, bring with them quite pure information about what produced them that allows us to study their sources. When it was announced, it was indeed, we thought it would be a story, but I think we had no idea how interested the public would be, how interested the press would be. And this is just a subset of the front pages that carried the discovery announcement in February last year. And you can see it was global front page news, from the UK to Spain to Germany to languages I don't actually quite identify. It really was big news around the globe. And to make a discovery like this took an international collaboration. The detectors are physically located in the United States, in the UK, and in Scotland and England, Wales. We're partners in this. But there are about 1,000 scientists from 14 countries, all contributing to this detection. Of course, you can't please all of the people all of the time, and this is what Private Eye had to say on the subject of the discovery. A huge black hole opened yesterday in the public's understanding of what the latest scientific breakthrough was all about. No light was shed at all by a huge, dense mass of newsprint that collapsed in on itself as it attempted to explain the importance of gravitational waves. The amount the public understood about the subject was so microscopically small that at first instruments could not detect it. But after refinement, the comprehension level measured less than a billionth of an atom. Said one hurt astrophysicist, "This could be the most significant lack of understanding since the last thing the public didn't understand." However, a member of the public was quick to congratulate the scientific community. "Look, we're happy that you're happy, and I'm sure the whole gravitational wave warp factor thing will help us defeat the Klingons and destroy the Death Star." Anyway, that was jolly good. This was actually sent to me by a senior member of our funding body. Fortunately, she has a sense of humour. But it's a salutary reminder that as scientists, we have to work hard to try and explain to people what we're doing, why we're doing it, and what the importance of it is. And in this case, again, there's multiple reasons why we're doing this. The pure one is to do astronomy. It was not just to make this detection, but to develop this technique as a way to study our universe. And in fact, that first detection was just the first in a period of a few months, again, where we announced a second detection in June this year, which was actually made on December 26th in this part of the world. Actually, on Christmas Day in the United States, the signal arrived. And in between those were large signals that we were confident about claiming as detections of gravitational waves. There was another signal, a bit smaller, which we're calling a candidate event, but which was also consistent with a pair of black holes colliding far out in space. So we're actually starting to have a family of these systems. And in fact, they are unusual in many ways. With astronomy, this is a plot that shows us using studies of X-ray signals, again, the information that we had before our detection of things that people thought might be black holes and what their masses would be, between about 10 and 20 times, 5 and 20 times the mass of our sun. The very first things that we detected were black holes of large mass, again, tens of solar masses, again with a final black hole of 62 solar masses. We're starting to see a family of these systems, again potentially completely dark, with no other way to study them. So a quick recap, where are we? Well, gravitational waves you can think of as a strain in space, space being stretched and compressed, with those waves travelling out a bit like ripples on the surface of a pond, but going in all directions. Why are we interested? Well, fundamentally, it's a new way to study our universe, to study dark objects, objects that don't emit light or electromagnetic signals. And as we'll see, the dark universe is an interesting place. And so I'll talk a little bit now about how we can see these on Earth. So this is a very pure motivation to study our universe. As we said earlier, when Einstein came up with his theories of relativity at all, they were pretty abstract. Again, difficult to explain to people what relevance those could have to everyday life. But now we take for granted the fact that we have global positioning systems. We have sat-navs in our cars. If we're lost, we can easily find our way. GPS is a multi-billion-dollar industry every year, and it does not work without putting in corrections for the signals that are being transmitted, corrections due to special and general relativity. So today, this is a very pure aim. In future, who knows? So how do we see these here on Earth? Well, let's look more closely again at the effect of gravitational waves. We said they stretch and squash space. So let's pick a patch of space on the board. And we've drawn a grid on the board. And a gravitational wave produced far out in the universe that's travelled across space, it's hit our solar system, it's come in, it's hit the Earth, it's travelling through the lecture theatre and going into the board, would stretch and squash points on the board just like this. And you can see it's a very characteristic effect. Distances are stretched in one direction whilst they're squashed in the other, and vice versa. And physically, that's what happens. It changes the distance between points. However, this is hugely exaggerated for effect, and it doesn't change them anything like as much as I've drawn there. It means these are challenging experiments for points, for objects separated by about a metre, as they were on the board there. A typical gravitational wave, if we calculate from general relativity what we expect, would only stretch those 2 points by about 10 to the minus 22 of a metre. What size is that? Well, the width of a human hair is about 50 microns, 50 times 10 to the minus 6. Size of a typical atom is about 10 to the minus 10. So a millionth of the size of an atom is pretty much how much 2 points would be stretched by. So these are very challenging experiments to be able to make instruments that can measure that. We need a very good measuring instrument, and we use light to do that. We take light from a laser, and we split it into two, essentially a half-covered plate. We send it out in 2 directions, bounce it off mirrors, and send those 2 light beams back to add up again at the beam splitter, and we look to see what happens. How does that help us? Well, remember, one of those mirrors is going to be stretched out, while the other one is going to be squashed in. So we're measuring the change in their position. And we do that using the fact that light's a wave. So we can think of light as a wave travelling out in this arm, bouncing off this mirror and being reflected back, whilst a wave travels out in this arm, bounces off and is reflected back. And if those 2 waves travel the same distance and come back, they add up again to form a larger wave. We'd see a bright spot. If, on the other hand, a gravitational wave passes by and changes the relative lengths of the arms, it stretches one, so one wave travels a bit further, squashes the other wave travels a bit less. They may come back with one wave as a peak, one light wave as a trough, and cancel one another out. We see a dark spot there. And so fundamentally, by monitoring the brightness of the spot here, we can look for the effects of gravitational waves shaking those mirrors. And that's the principle on which our observatories are built. As you might guess, many things, however, can shake those mirrors, or appear to shake them, more than a millionth of the size of an atom, in fact. And this is a list of some candidates, and I won't go through them all, but the most obvious ones are seismic noise. If we just plonk the mirrors on the ground shakes much more than a gravitational wave would shake the mirror. It's relatively easy to isolate against that. We take our mirrors and we hang them. We suspend them as pendulums. That makes a mechanical filter. The suspension point of a pendulum can move quite a lot. The mirror is isolated from that. And if we stack up our pendulums, it's even better. What we cannot isolate against is something called gravitational gradient noise. So sadly, Newton comes back to haunt us at this point. We've carefully taken our mirror and we've hung it and isolated it so that the ground is not shaking it, but it has some mass. And then a person, also with some mass, some distance away from that mirror, walks past it. Newton says if you have mass 1 and mass 2 and a changing separation, there's a changing gravitational pull. And so Newtonian gravity, objects moving around our detector will start to pull on the mirror again, and at low frequencies. That is a limiting noise source for us. Low frequencies because people move slowly. Again, they don't run 100 times a second back and forward past our instrument. Again, 10 times a second, 10 hertz is where the problems. Below that, things start to be a problem. And for that, in fact, we need to put detectors in space to get away from that. It turns out the effect of gravitational waves being a strain gets larger if you separate the objects that you're trying to measure. And so to beat these, it turns out we want to make detectors large, and that's what people have done. The 2 LIGO observatories that made the first observation, again, are large instruments. You can see a picture here of the Hanford Observatory in Washington State, the Livingston Observatory in Louisiana, and these are managed by Caltech and MIT in the United States, but as part of the collaboration, the LIGO scientific collaboration, this international collaboration working to design, operate, and analyze the data from these instruments. To do so requires technology that's right at the forefront of what you can do with measurement technology, in lasers, mirrors, control systems, a whole bunch of things. So it took, again, an international collaboration, again, to do that. Now, a little bit more detail of what the sites look like. This is the Hanford site. It's actually on the Hanford Nuclear Reserve in the United States. And I think just off in the distance there, you can see a dome. There are nuclear reactors still there. I think it's where the nuclear material was made for the bombs in the Second World War, but now it's mostly nuclear material for medical purposes, I think. Out there in the desert then, you can see this very large device. You can see these long interferometer arms and a center station about the size of a large supermarket. Again, and those arms are 4 kilometers long. So we can see, again, along the second arm there, 2 kilometer center station. And this is the Louisiana site. Again, it's a very different environment. It's about an hour from New Orleans. You can see it's out in the swamp in Louisiana. It's a beautiful site. You can see these pulls up the arms of the instruments. Again, these are large civil engineering challenges. To build this, again, required building up the instrument on banks. And to do that, earth was dug out, again, along the arms here to build the banks, to build the instrument on. It turns out if you dig a hole in a swamp, it fills with water. Shortly after that, it fills with wildlife. And again, at the end of actually this arm, for many years, there was a pool with an alligator, turtles. Again, it's a very beautiful site to visit, very interesting. So those are the sites. And when you do science on this scale, again, as well as the fundamental science, it turns out there are additional challenges that typically one doesn't think about when doing fundamental physics. So these are all pictures from the Hanford site. You can see here there was a wildfire, and it actually scorched right up to the instrument. You can see that's one of the long arms, and there's a concrete cover. Inside that concrete cover, there's a metal pipe, which has had all the air sucked out of it, that the laser beams are fired down. And you can see this actually acted as a fire break. The wildfire scorched right up to the end there, so burnt tumbleweed. These are some of my colleagues gazing thoughtfully at the wildfire in the distance, wondering precisely when they should leave, what they should do. Turns out it was all fine in the end. I said it was on a nuclear site, and indeed it is. And one night there was a security alert, security drill, security guard got up, got out, got into his car, set off across the desert in the dark, forgot there was a 4 kilometer long scientific installation in the way, drove straight over the top into the concrete beam tube covers, which you can see are there for a reason. The detector was fine. He was fine. His car, on the whole, was not fine. But these are just a set, and these are just some of the additional challenges that in studying the tiniest vibrations of space from black holes colliding 1.3 billion light years away, that have to be built in, that people often don't think about in big science projects. It's a very different world. Okay, so that's the 2 LIGO observatories, again, which have been operating. They turned on in 2015. Shortly, there'll be another detector located in Italy, but again, a European collaboration, France, Italy, the Netherlands, Poland, the Virgo instrument. In the UK, we're partners in LIGO. We also have our own smaller instrument in Germany, GEO 600. There's another detector under construction currently in Japan called the Kagra detector, which should take data about 2018. And actually, very recently after the detection, the Indian government announced that it would help locate a 3rd LIGO instrument in India. So there's a network of these instruments either operating or planned. And it is indeed important that there is a network for scientific reasons, because these gravitational observatories are not pointable. They're not like telescopes where we can look at a certain portion of the sky. They have some sensitivity to the whole sky, which is both good and bad. The bad side of that is it means we can't tell with one instrument. We can't easily tell where a signal came from. And we use timing, arrival times of the signal at different detectors to be able to tell where in the sky a signal has come from. So in fact, for the first detection, it actually, and they're quite proud of this, hit the Livingston Observatory first, and 7.3 milliseconds later, it hit the LIGO Hanford Observatory. So that gave us some information about what direction that signal must have been coming from. But with only 2 instruments, it's pretty weak information. And we do want to be able to do that. We want to know where they came from, because despite the fact that 2 black holes colliding may give out no other signal than gravitational waves, some of those other sources I talked about will. And we want to be able to work with our colleagues in the astronomy community to get them to point telescopes to see all the messengers that come, again, from individual sources. And in fact, what we do is we take the gravitational wave data, we look to see if anything interesting is there, we check that the instrument was operating properly, and then we send that information out, again, to our astronomy colleagues. The challenge is, as I say, with just 2 instruments, we don't give them very accurate information. We need the other detectors to be able to improve. And to show you what that looks like, this was our best estimate eventually of where that first detected signal came from, looking at the sky, somewhere kind of in there. Now, if you have a telescope, that's not a very satisfying thing to be told, well, if you point it somewhere in here, maybe we might be able to see something. And in fact, earlier in the process, when we were sending out signals, we didn't even do as well as that. We said, well, somewhere kind of in here is where you should look. To their credit, our colleagues, again, who are working hard on this with telescopes, with optical, radio telescopes, worked hard. This is kind of a blow-up of a little portion in there. Each of these patches is a portion of the sky that they tiled, basically, and tried to cover in the optical, in the X-ray, and the radio. And as it turned out, this was not right when we looked more closely. It really should have been here. But people did work quite hard in tiling. But it's not efficient. It's not a very satisfying way to do things. We really need to be able to pinpoint where sources are coming from. This is for all 3 of the events, the 2 and a bit events we saw, huge portions of the sky with just the LIGO observatories. Even if we add 1 more, we add that detector in Europe, you can see the uncertainty shrinks, and for that first detected event, we would have done much better in telling people where to look. And in fact, what we're heading towards is a global network that looks a bit like this. By about 2020, we should have this network of detectors, and you can see by timing when a signal arrives at the different ones, that gives a huge improvement, and we've quantified that in terms of how well we could do. But what's also notable is that they're all in the northern hemisphere. It would be really scientifically helpful to have one in the southern hemisphere. And when you do the optimization and you look at where you'd like to put one, it turns out Australia actually would be ideal to have an instrument there. And again, from the fundamental physics side, there's a whole set of questions, and I won't go through them, that these kinds of observations can help us study. Not least the fact that we know not only is our universe expanding, it's accelerating in its expansion. Again, and we know that from electromagnetic observations. We may in future be able to use these chirps, these black hole chirps or colliding neutron star signals, to give a measure of what gravity tells us about the acceleration of the universe. A whole set of questions in astronomy and astrophysics. So now, what are we doing now? Well, the detectors were turned off in January, again, to try and improve their sensitivity, because although we turned them on and they were better, again, good enough to make a detection compared to their first incarnation, there's still some way from their design sensitivity, about a factor of 3, which it turns out makes a big difference in terms of how often we expect to see events. Again, once we get to design sensitivity, we hope to see perhaps a signal a day from these, just from colliding black holes. We'll work with the other instruments. We'll look for signals from these other sources. However, nobody ever really met an astronomer who felt they had a big enough telescope and could see far enough. And there are reasons, and I showed you the plot earlier, why there's a whole spectrum of sources that we would like to study, both with improved detectors on the ground, but again, there are good reasons to want to put a detector also in space to work together with that. Because remember, I said everything I've talked about so far was just here. Just as an example of what we could do in space, there are other sources that, again, it would be very interesting to study. This is a picture of the Andromeda galaxy. And at the centre of the Andromeda galaxy, we think there's a black hole, but not this time a few times the mass of our sun, but a supermassive black hole, hundreds of thousands or millions of times the mass of our sun, an enormous black hole, as we think there is at the centre of our own galaxy and many other galaxies. This is a picture of the Mice Nebula, which we think is two galaxies in the process of colliding. And there are many people who study galaxy collisions. And here's a simulation of a galaxy collision. The two galaxies come in, they see one another. If we stop there and compare it to the Mice Nebula, you'll see it looks very similar. We can let it keep running, and you will see the galaxies don't just pass through and keep on going, they actually merge in the simulation here. And if we do that again, but this time we strip off the stars from the outside, we look at the supermassive black holes in the centres of the galaxies. They've become caught in one another's gravity. They're spiralling in, producing gravitational waves as they do so, until these supermassive black holes collide and emerge. Now, that's a source we would not be able to study on the ground. For that, we would need to put detectors in space. And indeed, the European Space Agency selected the gravitational universe as the subject for one of its future large mission launches to put a detector in space, this time not with a few kilometre arms, but perhaps 5 million kilometre arms, a triangle of spacecraft with laser beams fired between them, following the Earth around in heliocentric orbit, this time measuring the change in separation of the spacecraft as that happens. As you might imagine, taking this technology and flying it, again, to make these measurements is as complicated as testing things on the ground, if not more. So in fact, there was a demonstrator mission called LISA Pathfinder, not to detect signals from space, but to test the technology needed for a future mission. And that was launched again at the end of last year. It worked exceedingly well. Again, a beautiful demonstration of some of that technology, again reported this year. So we're heading towards a situation where we expect to have a network of detectors on the ground. We're working hard on understanding the technology to make those better, and I haven't had really the chance today to talk about the technology again, which is highly sophisticated and itself has a bunch of spin-offs, and also looking towards a detector in space. Again, the current mission launch date is, I think, 2034. That was before both we made the detection and the technology demonstrator, so who knows, again, if we're lucky, that might come forward. And why is this interesting? Well, again, when we think about how much of the universe is made of stuff that we understand, it's a few percent. We believe there's stuff out there in the cosmos that we only detect through its gravitational effects, doesn't give out any light. Again, we call that dark matter, but currently we do not know what that is. We know, again, that the universe is accelerating in its expansion. We say that's caused by dark energy. We do not know what that is. Again, we need new physics to help explain what we observe, particularly around the area of gravity. These beautiful pictures are of the universe in different electromagnetic wave bands. Every time you turn on a telescope, you see something different. The first discoveries we made with gravitational waves actually were a surprise, and so, again, I look forward to seeing what more unexpected things gravitational waves will tell us, and I will stop there.
Thank you, Sheila, for this very inspiring talk. Other questions or comments from the audience?
Looking at the graph you showed there, and you said that you did detection in September and October,
Yep.
and January and December.
The detections were, I think, September, October, and December.
Yeah. So then your arc curve going from in right ascension, that's about 24 and 0 to 1, and then you skip. You're missing 4, 5, 6, and then you're missing 2, 3, 4. And then you make recordings of 5, 6, and 7 in right ascension. Now, why is there no recording between September and October, say November? Why is there no recordings in November, only in December and January? If you're 90 degree of an arc there.
So I think I'm not quite understanding.
Right ascension is 0, is spring equinox. Down to 6 is summer solstice, or the summer coordinate. So you have a sweep. The Earth is going from spring to summer, and you're making a recording, obviously. So why, it would be from spring to, from September to December that you're making the actual recording.
That's right.
So it's from autumn to winter.
Yep.
On the sweep. So that's 90 degrees. And you seem to be missing the November part, the center part, for recording of this object.
Okay,
Why would that be happening?
So I think I'm still not quite. So when we make a measurement like this, and we run for say 4 months, as we did,
Yeah, you're making a measurement of an object 1.3 billion light years out.
and we measure it once, we measured that the signal came, but it's not. So that signal, it comes in from.
It's a 30-kilometer object.
Yep.
They are 366
Yes.
kilometers side by
Yes.
side, and it's sending out the signal all the time.
No.
Or does it stop?
No. So it only is big enough for us to detect when the two black holes are in their last few cycles, and then they collide, and then the signal dies away. So that chirp that I showed you, that signal that came in, lasted less than a second. So it's a transient event.
So are you getting a signal when the two black holes are aligned in parallel or in an axis north-south or east-west?
So in this case, it's pretty much, I think, as you see there, they were pretty much face on to us like this.
Those are east-west, the axis is, when we're looking at it.
Well, they rotate, I don't quite know how to say that in astronomical language. For us, looking from the Earth, when it arrived, the signal was the object was the system was oriented like that. That's right. They're apart, but
Right.
that whole signal.
How then do you get another signal, if you're saying it lasts a second, how
Yep.
do you get another signal 3 months later?
Because it was another object, another collision of a different system.
Right, so it's 2 different objects in the universe we're talking.
That's right. 2. Well, actually, in the end, we think probably 3, but that was the first one, the one that I showed you the data for. The other one we published was this one, but a different signal.
So when you said the astronomers were looking out and making the grid shape,
Yes.
whereabouts were they looking at? There's 3 different objects,
They-
they're 90 degrees apart, so why aren't they 90 degrees apart on the...
They looked in different places for the different objects. So that first object, they actually looked, it itself, let me find the patch on the sky again. They actually looked for any kind of counterpart from that first object. Actually, they started a few minutes after we told them to, and then actually they kept looking for a couple of weeks, just depending.
Okay, so could we say there are galaxies out there that these black holes are in, and that they are they in the area of space where there's no galaxies that these 2 black holes are occurring in?
We don't.
What is it?
We simply don't. We aren't able to tell well enough exactly, whether they were located in a galaxy or whether, as seems perhaps likely, they were in isolated space with nothing around them because they'd already eaten whatever was around them as isolated objects. So it seems likely, we can't tell exactly, but it seems likely they were somewhere with nothing around them, no dust, no gas, they'd eaten whatever was there, so there was no electromagnetic signal measured. People looked, and they looked for a couple of weeks but didn't see anything, and they did the same for the other 2 events.
Thank you, and thank you for a really very clear talk. Just following up on your last comment, and you mentioned during the talk as well that you would expect these to be dark events. And there was a report maybe of a marginal detection.
Yeah.
So what's your view of that?
Well, it was a marginal report, and it wasn't big enough, I think, that one could have confidence that there really was something there. I think the statistics were what they were. So it's consistent with nothing, basically, consistent with there being no electromagnetic counterpart.
Moved out by integral, certainly.
Right.
The
the thing I was interested in, the two black holes that collided in the initial observation, do we know the relative spin axes of those two to each other? And would it make much difference if they were, say, 90 degrees to each other, or even spinning us up in opposite directions?
So for those ones, we could not constrain very well. We couldn't tell very well the spin of the individual black holes. In fact, we could tell the final black hole, but the individual ones, the signal that we got was consistent either with some spin or with no spin, and you couldn't really make a statement. I think for the second event, we could make a statement that one of the two that merged was definitely spinning. And yes, there is information that tells us about the history of the systems, potentially, from the spins of the individual black holes. Again, about the possible routes by which they formed, whether or not the spins were aligned or whether or not the spins were misaligned. Again, can carry with it information about the formation channel, about whether they formed independently and then at some point later came together, or whether there was a binary star system, again, in which the two black holes were then formed. So there definitely is information to be got out of the spins.
In the early 80s, I was a visitor at Caltech with Dr. Drever and a quantum mechanic called Carlton Case.
Yes.
And we were concerned at the time about the reduction of thermal and quantum waves.
Yes.
The resonant detectors of the Weber type,
Yes.
as well as interferometers.
Yep.
We concluded at the time that the use of squeezed quantum states
Yes.
would be beneficial in reducing below the standard quantum limit.
Yes.
In these past 30 years, has any progress been made?
There's been a lot of progress made, and again, I'm sorry I didn't get to talk about the technology, but yes, there's been a lot of work done on the generation of squeezed light, several dBs of squeezed light now generated, and in fact, the interferometer in Germany, the geo-interferometer, has now been running for several years with squeezed light, with an improvement demonstrated in its high frequency sensitivity of several dBs due to the application of squeezed light. And in its next stages, again, the Advanced LIGO instruments, the plan there is to implement squeezed light on those. So yes, there's been a huge amount of work in that area, and it's fascinating work, again, because if we think about quantum, didn't talk about the technology, we think about quantum effects as being only things that are big and things are small. In these instruments that are 4 kilometers long, the mirrors that I talked about are not small, they're 40 kilograms of ultra pure glass. And they, when we get to design sensitivity, will start to behave like quantum objects. But quantum objects that are massive, it's really macroscopic quantum mechanics. And again, it's an amazing field.
Yeah, at that time, the techniques were called finite dimensional quantum electrical network theory and thermal field dynamics. They were being used to study work. And Dr. Drever at the time had also developed some isolation techniques.
Yes.
For these resonant detectors. What happened to resonant detectors?
So resonant detectors, again, I didn't talk about those. A precursor to these instruments was the idea of building an instrument, a bit like a bell, kind of, but basically large bars of metal, of aluminium, a big cylinder. And that cylinder has a resonant frequency, a bit like a drum. It has a mechanical resonance. And so the idea is to monitor that and look for excitations of the bar from gravitational waves coming through. However, the resonant detectors, on the whole, are sensitive over a quite narrow range to frequencies around that resonant frequency. Whereas these detectors, I spared you the curves, but they're actually sensitive over quite a broad frequency range. And techniques moved on to the point where, with these interferometers, we could reach sensitivities on the whole better than the resonant detectors. So resonant detectors actually have performed over the years a service by running continuously, very reliably, but on the whole, the interferometers have really taken over. Key to this, and again, I didn't talk about this, is the isolation of those mirrors from all external disturbances. So not only are they ultra pure glass, they're suspended on 4 glass fibers, each one of which is about the thickness, again, a few times the thickness of a hair, and hanging to reduce the thermal noise. And again, it's my personal research area, one I have interest in, that the group in Glasgow has worked on for many years, on the mechanical isolation of these systems. Very sophisticated technology. Thank you.
Yes, so in 2020 or thereabouts, when we have the full array in operation, and the sensitivity presumably evolving, even the existing instruments will improve, what ultimately, in terms of spatial resolution, will we be able to achieve in the sky? Because this is very important for one of the assumptions.
So if you'll forgive me, I will open up another talk and see if I can find you a plot that has that on it, and that one won't do. There we go. So I can show you with 3 sites. So this is for neutron stars, but it'll be broadly equivalent, I think, for black holes. That would be with the 2 LIGO sites, and 1 site in Europe. And you can see again, even with 3, we still get these large uncertainty contours. And you can see these are 90% confidence error boxes with a median of more than 20 square degrees for just with 3 sites. If, on the other hand, we go to the 5-site picture, you can see how much that shrinks. It shrinks considerably. So that's, again, I don't know exactly the number there, but you can kind of eyeball the difference that makes. And even with 3 sites, there were some red X's. There were areas of the sky in which we have no sensitivity. Again, once we go to 5 sites, we really are sensitive to the full sky.
But it's not only a function of the number of sites and tracks.
It's how far
but
apart
also
they are.
the time resolution and the signal to noise as well.
I think
You can get a better pointing.
I'm not sure it's time resolution, the ability to measure the timing yet, that limits us. I would have to check that. I think it really is the space. Well, it's related to time, I guess, but the physical spatial separation around the globe that we want, and it's why putting one in Australia. It's not just the distance away, but it's one of my colleagues in Glasgow, Martin Hendry, has written a paper actually on doing the optimization problem, starting both with a blank sheet of paper with no sites, where would you want to put one, and with the network we have, where would you want to put one? And in both cases, you want to put one in Australia. So I think that partially answers your question.
Could you say something about the potential for detecting signals of cosmological importance back out to the microwave background?
Sure. With these instruments, we won't get to see signals from the earliest universe. Again, with the next stage of ground-based instruments, another factor of 10 in sensitivity, we basically should be able to see black holes back to, out to Z equals a very large number, essentially do a full census of black holes throughout cosmic history. To get to using ground-based detectors to get to signals from inflation, again, I think even with the next generation of ground-based detectors, we're probably still not quite there, but it remains it's a long-term goal of the field to get to that point. Again, but it would still require technological improvement beyond that to get to the scenarios that that cosmologists think are plausible. You can cook up some less plausible scenarios where we might see something, but to get to the sort of plausible scenarios, we need to go quite a bit further.
What about follow-up observations? Presumably, the observers are looking at areas of the sky for a single black hole resulting from the merging of the two.
But again, if it's sitting there being a black hole just spinning quietly in empty space, I think you would not expect particularly electromagnetic signals.
Indirectly, maybe from
Perhaps if there's matter around it to interact with. And again, it's why it was worth looking, even with this is the first binary black hole collision anyone's ever detected, and who knows what environment it was in, and it might have had, it might have had matter around it that we might have seen a signal from. We didn't, again, with the collision. So it seems maybe unlikely we'd see anything, again, associated with the final black hole.
Does the signal that you detected produce a black hole of a certain size?
Yes, 62 solar masses.
This discovery was to some extent unexpected. So in this regard, Do you think to revisit the scientific objectives for next generation instruments, or it will be the same as like before this detection?
That's a very good question, and actually we are at the moment, I mean, the scientific prospects have got nothing but better, I have to say, and more exciting, because this was a very speculative source, you're right. I mean, there was a huge range of predictions about how often something like this might happen, which ranged from never in the lifetime of the universe to actually quite often, but they were very speculative. And so in fact, almost every plot that I could put up here from pre the detection will talk about neutron stars colliding, because at least people had seen binary neutron stars, so we knew those systems existed. People have worked quite quickly again and have already published papers on what this implies about the science that we're going to be able to do, and it's very exciting in terms of studying, again, the family of black holes that we now think, black hole binaries that we now think may exist out there. The realization that with a space-based detector and a future detector on the ground, the space-based detector may see the early evolution of these systems and be able to predict when and where in the sky the coalescence will happen several years later in the band of the ground-based instruments, and we would know years in advance potentially that this signal was coming. So plotting the sort of life cycle of black holes of various masses, again with both space and ground-based instruments, working again with things like SKA, LSST, the future big electromagnetic astronomy instruments. The rate at which we can see these, if it really is one a day, when we get to even just to design sensitivity of our current instruments, starts to turn us into a survey instrument for binary black holes. So those are all things that people are, again, thinking about the implications of and working on in terms of a future network of detectors. If we make them more sensitive, really what additional science are we going to be able to do?
And what about the previous objectives? So they are still alive?
They're still alive. Again, of course, when I talk about, again, the neutron star systems, our knowledge of those has not changed. So we still have the same expectations for binary neutron star collisions. Again, that's an area where, again, there still exists a spectrum of possible rates. We don't know how often those are going to happen. We didn't actually expect to see anything in our first run, but if we were lucky, we might see two neutron stars, but it would be a bit unlikely. For the next run, the target was, well, we start to get into the interesting possibility of seeing a binary neutron star collision. Also, pulsars, again, and pulsars are signals that are there all the time. Again, those are ones where we would expect continuously the signal to be there. But it's probably small, but that means what we need to do there is run the instruments for a long time, integrating up the data, integrating down the noise whilst the signal remains. So we only had a 4-month run for that first run. The next run, which by the way is due to start in December this year, should be for 6 months. Once we start to add that data together, it becomes very interesting to look for the pulsar signal. So the other sources, nothing's changed. We still expect those to be there.
Sheila's answered my question.
Other questions? Oh, yes.
If the black holes are merging and they're going faster and faster, why are we only getting sub-second signals when they should be going to from hundreds of hertz to kilohertz and higher?
So again, the frequency that we get depends partly on the size of the individual black holes, and again, in one of the other plots I have, I can, if you like, show you. Again, if you forgive me, I'll just open up and see if I can find for you pictures of the individual signals. No, failed. Okay, you know I said we got those 3 signals. The first one of those, we just saw the last few cycles and then a large signal. Sort of after, for the second event we actually got many more small cycles and then a collision. And so the frequencies that we get depend on the size of the objects before they actually collide. So some smaller objects could collide and go to higher frequencies. So the size of the objects here that set, again, the sort of frequencies that we saw from, again, sort of tens of hertz up to, I think, about 250 hertz or so, a few hundred hertz. But it just depends on the size of the objects. And that's one of the things that told us it had to be black holes.
When you receive a signal such as you did a year ago, and that signal has travelled, these waves have travelled through the universe for 1.3 billion years.
Yes.
Is that a pristine or uninterrupted signal? I can imagine other cosmic events equally producing waves. And would these other waves impact upon the signal that you received? And how do you cope with that and eliminate it from your observation?
So in cosmological terms, although this sounds like a very long time ago to us, and it was, again, 1.3 billion years ago, multicellular life was just kind of getting going here on Earth. In cosmological terms, it's actually not all that far. If we go out to further distances, out to cosmological distances, we do have to start to worry about gravitational lensing. And again, that's an effect that can build up over long distances that could distort our signal. Over this kind of distance, I think we don't think lensing's an effect, and we would, I think in this case, not expect much to have interacted with the signal before it got to us. In principle, if you had many, many sources within a certain volume that you were sensitive to, you do get to the point where you'd be confusion noise limited. And in fact, for some sources, the space-based detector will be in that position. For white dwarf binary systems, there'll be so many, it will be difficult to distinguish them. And that's a data analysis challenge. We're not in that regime here.
Two last questions, one up there.
Thank you. Just back to the mechanics of the observatory itself. You said that the distortion in space-time is something millions of millions per width of an atom. Can you give some intuition as to the mechanics of how we can see that?
Okay, so there's a whole other talk on how the detectors work and how the technology works. Again, the basic principle is the one that I showed you here. Okay, and so I can talk a little bit around this. We literally use the wavelength of light in a way as our measurement here. And that if one of these, and they're 40 kilograms ultra pure glass, if one of those moves, if he travels a different distance and comes back, and you can see we go from completely bright to completely dark in the space of, half a wavelength of light. It's still big, but that's completely bright to completely dark. So we're just measuring changes in intensity. And I skipped over a whole bunch of optical tricks that we use. The first thing we do is we make them big. So instead of having to measure 10 to the minus 22 of a meter, at 4 kilometers, it turns out, we only need to measure 10 to the minus 18. Every order of magnitude counts. Let's not sniff at that. And in fact, for the next generation, the plan is potentially to make them even bigger still, because it's one of the simplest ways to make the instruments more sensitive. We then use a whole bunch of optical tricks. We artificially make them longer, effectively, by not just having a simple optical system like this, but we put another mirror here and another mirror here. And these form cavities in the arms of the instrument, so the light bounces many, many times. So if a mirror moves, instead of just being sensitive to how far one light beam has to travel, it's multiplied up by the number of n, the number of bounces. So we put highly reflective mirrors there and there. We then do a bunch of other things. We actually, rather counterintuitively, put another mirror here. And it turns out what that does is forms the whole instrument makes another optical cavity, which is a bit like having a higher power laser. And that makes the fringes effectively steeper. So I skipped over, again, the noise sources at the top there. Photon shot noise is one of the limits. And that means as we measure the brightness here, we literally stick a detector here, and we measure the light coming out. We measure its brightness. I just told you could think of light as a wave, but of course, you can also think of light as a series of particles, of photons. So we're effectively counting photons coming out the output. the effect, and there's counting statistics. It's quantum mechanics, and I glossed over a whole bunch of stuff there. But it's photon counting statistics, counting the photons coming out. That effect gets better, is less of a problem if you turn up the laser. So being thrifty Scots, we didn't want to waste the light, and this, I think, is very important. We didn't want to waste those photons. So instead of any light going back towards the laser here, we put a mirror there and resonate that up to help with that. We then, because doing it with mirrors is clearly a good thing, we sneak another mirror in here, and as a gravitational wave goes by, what it does is it shakes these mirrors at the gravitational wave frequency, so light comes out at that frequency. If we carefully position a mirror here, we can build up that signal and make it bigger. So I have another plot that goes from this to a very complicated optical system, which is much more like reality.
One last question over there.
Thank you. A millisecond pulsars, it's a very old idea. Is it still an active area? Any chance to get a detection, say, in 20 years?
Oh yes, I think with pulsars, oh yes. I think they're going to be a very interesting research area. Now, at higher, if it's millisecond, I guess, yeah, I mean, it's still something that we could look for, but I think pulsars are going to be very interesting.
Okay, very much. I'll add one more. Thank you very much. The LISA spacecraft will have 3 detectors. What sort of directional information will you be able to get from those 3 in terms of the source?
So I can't give you the numbers. There is, however, LISA, there is an antenna pattern for the instrument. So it does have some directional sensitivity, because if we look at the orbit, you'll see on its own there's a triangle, but that triangle both rotates around the sun, and actually you'll see when I run it, these 3 spacecraft also rotate on their axes as it goes round. So that's actually inclined in a plane, so there's actually an inclined orbit as it goes round. So certainly for signals that have any duration, again, there is an antenna pattern with some directional sensitivity, but not, I think, equivalent to what we can do on the Earth.
Okay. So in the interest of time, let me conclude the session here, but let's thank again the speaker for a very enthusiastic and inspiring talk.